This video will walk you through the Unit 7 test review and provide explanations for every single problem within it. Let's first start with the first three problems here, which involve writing expressions from radical form into exponential form. The way that we do that is to take whatever's underneath the radical sign. We're going to go ahead and pull that out as our base. To turn all this notation into an exponent, it's really simple. The power that the radical is raised to is the top. The root is the denominator of the exponent. So we can rewrite this as 5a to the 5/4 power. Same thing in number 2. I pull out the 3n from underneath the radical. My exponent, power goes on top, the root goes on the bottom. The exponent would be 7 over 5. For the last example, same idea. Pull out the y plus 4. Now you'll notice you don't see a number with the root. Just remember there's an invisible 2 when it comes to writing a root without a number, as the second root is the lowest you can go. So my exponent for this would be 9 over 2. Now the next set of problems involves you going the opposite direction, which is take something in exponential form, write it into radical form. So we'll start with 3r to the 1/2 power. 3r is going to go underneath the radical symbol. Now, this particular problem, you could write a couple of ways which would be acceptable. The bottom number of the fraction is the root. The top number is the power in which it is raised to. So you could write this as the second root of 3r to the first power. However, we know the second root is the same as the square root, and we also know raising something to the first power doesn't really do anything. So the more appropriate way to write it would just be square root of 3r. Now we have x to the 6/5 power. X goes underneath the radical. It's a fifth root because that's the bottom of our fraction, and it's being raised to the 6th power. And then last but not least, we have x plus 7 to the 3/4. The 4 is my bottom number, therefore that is my root, and that whole radical will be raised to the 3rd power. This next section underneath says to simplify each exponential expression, then rewrite your answer in radical notation. So let's take a look here using some basic exponent properties. How can we combine these terms together? So in number 7, I have x to the 1/4 times x to the 2/3. If I multiply things with the same base, so that I'm multiplying two things with x's, I have to add my exponents. So to combine this together, I would have x to the 1/4 plus 2/3. Now, my suggestion would be, if you're really bad at fractions, use your calculator to punch this thing real quick and convert it. However, please do not write this as x to the 3/7 power. That is not correct. Remember, when adding fractions, you must have like denominators. So what I could theoretically do, a common denominator between quarters and thirds would be to take things to the 12th power. Or excuse me, to a denominator of 12. So 1 over 4 is the same as 3 over 12. 2 over 3 is the same as 8 over 12. So I can write this answer as x to the 11/12 power, which in radical notation would convert to the 12th root of x raised to the 11th power. Number 8 is the exact same type of problem. The only difference is we see that we have just a regular x. Remember, that has an invisible exponent of 1. I'm going to do the same thing I did in number 7. Since I'm multiplying with the same base, I add my exponents. So it would be x to the 3/2 plus 1. Again, use your calculator or use basics of converting fractions. I can convert this as 3 over 2 plus 2 over 2. This would give me the same thing as x to the 5/2 power, which I can then rewrite as the square root of x raised to the 5th power. Now, last but not least, we've got ourselves a basic fraction, same base over top of each other. However, we've got our fractional exponents. Same base on top of each other means we're going to subtract the exponents. So what we would do is write this as y to the 6/5 minus 1/2. Once again, I'm going to make a common denominator out of that. Common denominator between 5 and 2 is 10. So 6 over 5 is the same thing as 12 over 10. 1 over 2 is the same thing as 5 over 10. So this would simplify down to y to the 7/10 power, which in radical notation is the exact same thing as the 10th root of y raised to the 7th power. So you will see some basics on converting back and forth between radical and exponential form, and you will see a couple of exponent properties used. You can see the simplicity of these problems here. That should give you kind of an indicator as to what you'll probably see on your test. Now, if we look at the next section here of your review, next couple of problems involve simplifying basic radical expressions. You notice here we've got some cube roots. So if I want to simplify cube roots, you got to make sure you're finding triplets of whatever you're breaking down. So we talked about using factor trees for these. So let's take a look at number 10 here, where we've got two cubes being added together. So in order to add the same root together, you've got to have the same base. You've got to have the same number underneath the radicand, or radical symbol, excuse me. Right now we don't, so we're going to break these down. First thing we're going to do is break down cube root of 250, which breaks apart into 5 and 50. 50 becomes 5 and 10. 10 becomes 5 and 2. It's a cube root, so I need triples. Okay, I need 3 of the same thing in order to pull it out front. So I can rewrite cube root of 250 as 5 times the cube root of 2. Now I'm going to do the same thing with 54. I'm going to break that apart. That becomes 2 and 27. 27 is 3 and 9. 9 becomes 3 and 3. I've got a triple of 3's to pull out, so I'll have a big 3, cube root of the leftover 2. Now that I have the same root left over, both of these have cube root of 2's. Now I can add these radical terms together and come up with a final answer of 8 cube root 2. Number 11 is a little bit simpler because it's just simply finding one singular cube root. So all I'm going to do here is just simplify everything that's underneath of it as far as I can. So we'll start with 135, which breaks apart into 5 and 27. And we just broke down 27 in the previous problem. So here I have a triple of 3's. Now, when it comes to the variables, there's two ways you can do this. You can either draw a whole bunch of little factor trees, which I will do here just so you can see x to the 9th. That's the equivalent of having a grand total of 9 x's. Make sure I counted that out right. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I have 3 groups of those. And y to the 6th, which would give me 6 y's, which are also broken into 2 triplets there. You can do it that way, or realize that with exponents, you could simply divide the root from that exponent, and that'll tell you how many groups you have and also how many are left over. That's totally up to you, whichever is easiest for you to organize. So now what I'm going to do is take all my triplets and pull them out front. So I have a 3, I have 3 x's and 2 y's. So all I'm going to do from there is put whatever's left underneath my cubed root, which was just a 5. And that'll give me a final answer of 3x cubed y squared with the cubed root of 5 attached to it. Given that you've got exponents and radicals and different roots very close to each other, make sure you are writing them neatly enough so that your numbers don't get crisscrossed. And then I can clearly see what you are writing. So that's how you break down your cube roots, very similar to square roots. And we talked about this earlier in the chapter. Whatever your root is, that's just simply going to tell you how many of that same type of number or variable you are looking for when you break it apart. So that's some of the stuff from the early part of the chapter. We'll see some more that pop up with graphing just a little bit later in the review. Now we're going to take a look at some function operations, which you learned in section 7.4. So I give you 2 functions here. F of x is negative 4x plus 2. G of x is equal to x squared minus 5. We're going to do some basic operations, and we're also going to do some compositions. So let's take a look at number 12, which is saying add the 2 functions together. So just for substitution's sake, all I'm going to do is plug in my 2 functions where it tells me to plug them in. It's just simply telling me to add them together. All I have to do is combine like terms. So I have x squared, negative 4x, 2 and negative 5 will combine to negative 3. And I've got myself 2 added functions. Same thing with subtraction. Go ahead and plug in your 2 functions. The only thing you have to keep in mind with subtracting 2 functions is that the minus sign has to affect the function that comes after it. So the signs are going to flip for the g of x function. So I would make sure to convert those first, and then do the same thing you did in number 12. Combine your like terms. So I'll end up with negative x squared, negative 4x, and positive 7. Now, 14 and 15, this is where we get into composition. So that was a much newer skill that you learned earlier in the chapter. Keep in mind what this is telling you. You work your way inside out. So I have f of g of x for 14. What that means is I need to take the g function and go plug it in for f. So what I'm doing here is the g function, you see me just circling up above, is going to go in for the x as part of the f function. So it's going to look like this. Negative 4, instead of x, I'm going to plug in the g function. Once I do that, all you're trying to do is simplify it as far as you can. So distribute, combine like terms, do as much as you can until you can't go any further. So here I can distribute the negative 4, get negative 4x squared plus 20 plus 2. All I can do is combine a couple like terms. My final composition will give me an answer of negative 4x squared plus 22. Number 15 tells you to do g of f of x, which means since f is on the inside, the f will get plugged in for the g. So I'm going to take the f function, plug it in for x of the g function. So right off the bat, I'm going to plug in 4x plus 2 in the x part of the x squared, and then tack on my minus 5. If you see a function like this, please keep in mind, you can't just distribute the squared to both of those terms because there's a plus sign in the middle. Mathematically, you will not get all the correct terms. So what you have to do is write it twice, because keep in mind, if you square something, all that means is you're multiplying it by itself. As long as you do this, you're much less likely to make a common mistake. You write it out twice. We're going to go ahead and distribute this together. So that'll leave me with 16x squared, negative 8x, positive 4, minus 5. Combine your like terms, you get a final answer of 16x squared minus 16x minus 1. So those are the basics of your function operations, a little bit of adding, a little bit of subtracting, and some compositions. You'll definitely see a little bit of each on your test. If we look at the next page here, we've got ourselves some inverses. So let's talk about how to find an inverse of a function, and then we're going to talk about how to verify that functions are indeed inverses of one another. So you can see in 16 and 17, they're both written in function notation. Remember, function notation is a fancy way of saying y. So the first thing I'm going to do is replace f of x with a y. In order to find the inverse, first thing I'm going to do, swap the two variables. So x and y are going to trade places and nothing else. Then my goal is to get y by itself. So number 16, I'm going to add 3 to each side, and then divide by 2. So my final answer for an inverse would be x plus 3 over 2 equals y. I'm going to do the same thing in number 17. So first, replace f of x with the y, then trade the letters, then get y by itself. So to do that, I'm going to subtract 2. And then to get y by itself, it's being taken to a 4th power. So to undo it, I'm going to take everything to a 4th root. So, keeping in mind that I'm taking something to an even numbered root, we technically need our good friend the plus minus on the front. So plus or minus the 4th root of x minus 2 will equal y. That's how you go ahead and find an inverse of a function. Turn the f of x into y if you have to, then simply switch out the two letters, go solve for y by itself. Now in 18 and 19, you're being told to verify that given functions are inverses. In order to verify that they're inverses, you have to do compositions of each other. So in both 18 and 19, we're going to do two compositions. We're going to do f of g of x, and then we'll do g of f of x for each one. If they are indeed inverses, and you do the math correctly, you should get x every time you do this, if they are indeed inverses. If you get something other than x, that means your math is off. So, if I'm going to do f of g of x for 18, that means g is getting plugged in for f. So it's going to look like this. 3 times the g function, because that's getting plugged in for x, minus 7. Times 3 and divided by 3 will cancel out, leaving me with x plus 7 minus 7. 7 minus 7 will cancel out and leave me with x. Now I'm going to do the same thing, but do g of f of x. So I'm going to take the f function and plug it in for g. So f function is going to go in for x right in the top of the fraction as part of the g function. So right off the bat, again, I don't really have any distributing to do. So off the bat, I can see minus 7 and plus 7 are going to cancel. I'll be left with 3x over 3. 3 divided by 3 cancels, leaving me with x. This is all the work that I really need to see. I need to see that you can plug it in correctly and do some basic canceling to verify that it is indeed x. If you just tell me that it's going to equal x, you aren't getting the credit for this. 19 is the same idea. We're going to go ahead and do both compositions. So f of g of x to start, and then we'll go the opposite way and do g of f of x. So we'll plug the g function in for f. So it's going to look like this. So in for x, we'll go the x cubed minus 8 over 10. So first things first, the 10s will cancel because multiplying by 10 and dividing by 10 cancel each other out. So I'll be left with the cubed root of x cubed minus 8 plus 8. Minus 8 and plus 8 will cancel, so I'm left with the cubed root of x cubed. Cubed root and cubes cancel out, so I'm left with just the x. That means I've verified at least that direction. Now I'm going to go the other way, where the f is going to get plugged in for g. So we'll have the cubed root of 10x plus 8 cubed minus 8 over 10. Cubed root and cubed cancel each other out, so I'm left with 10x plus 8 minus 8 over 10. 8 and negative 8 cancel, so I'm left with 10x over 10. 10s on top of each other cancel. That leaves me with an x left over. Once again, fully verified. So again, to verify that two functions are indeed inverses, you're doing two compositions, one each direction. The goal is to prove to me that you can do the composition correctly and ultimately end up with x. The last couple of problems on this page are graphing problems, so this actually goes backwards to the very beginning of the chapter. You'll see one or two of these potentially. This is something I know most of you have done very well with. Just a quick review on how to graph these. Again, use your graphing calculators to your full advantage. We've got ourselves a square root function and a cube root function here. Let's talk about number 20. It's a square root function. When you punch that into your calculator, since it's a square root function, you are going to get a bunch of errors because you cannot take the square root of a negative number on a regular graph. That's its own different category of how to graph. The first handful of ordered pairs you should get are going to look like what I'm listing out here. So again, you want to list a few of these. I don't need a gigantic list, but list a handful of these to show me you've got the right values. So these are the few that come up when I punch it in. So it starts at -2, -5. -1, -4 is where it goes next. And then we start tailing off here a little bit. This is what your graph should look like. Now notice, you want to compare it to your calculator screen as well if you're not sure. Since this graph starts at -2, -5, I should see nothing before that or underneath that point, given the way this graph is constructed. So don't add extra lines or get sloppy with it. If your graph does not match the way that it should, you will not get credit for that. And that's an easy point to get because all it has to do is match your calculator. Now, in regards to domain and range, this is the type of graph that has to be a little bit more specific. So domain-wise, the leftmost value, I should say, is -2. And since that is a point, we are going to put a bracket around it. As I go right, it goes all the way to infinity, and we put a parentheses around it. Range, same deal. The lowest value is -5, and it is an included point, and it goes upward very slowly to positive infinity. Make sure you very clearly write the difference between a bracket and parentheses. If you get a square root function, that's the one you're going to have to take 2 seconds and think about. As you'll see with the cubed root graph I'm about to do in a second, that's the easy one where you don't have to worry about it as much. So here I have the cubed root of x plus 3. This graph will go on infinitely no matter what x and y values you try to find. Goal is to basically find where the graph has its biggest stretch. So that way you can easily plot the middle of that graph where it's going to stretch vertically, And that way you get enough points where you can clearly make a sketch that looks like it should. So few values that'll do that. -2 through 2 in this case will be fine. So these are the values again on my calculator that I get. Keep it in mind, -1, 0, 1, you see the biggest jumps, and then once I get after 1 or before -1, that's when the numbers really start tightening up. Again, you're looking for where do the biggest jumps occur on your table. That's where you kind of want to center your points, if you will. Figure out, take those points and then pull a couple before and after it so that you get yourselves a nice sketch. So, here we go with that. So, I'm going to plot the 3 easy ones. Again, eyeball the best that you can. And you've got yourselves your graph. Again, make sure you make it look close to what the screen says on your calculator. You don't want to have anything sloppy that I can't read or that doesn't look like the way that it should. It's tailing off in the wrong direction, etc. It's too easy of points to lose there. Now, here's the beauty of these functions. If you get a cubed root, domain and range, nice and simple. They're going to extend negative to positive infinity, both horizontally and vertically. So again, that's your quick refresher on how to graph. If you're not sure how to punch things into the calculator, that's definitely something you're going to want to ask me in person before you take your test on Wednesday. Now, we've got the last page of your review, which deals with, explicitly put some questions in about domains. Now, you won't see very much of this on your test, but I know this is a place that a lot of you struggle with on the last quiz. So I do want to point out a couple things when it comes to finding just regular domains of functions without having to graph anything, etc. Now, again, you can use your calculator to kind of figure this stuff out, if you will, but there are some key things that you can look for in these problems to figure out how the domain is going to work. So let's start with number 22. Y equals 3 over x minus 7. This is actually a problem just like ones that we saw in the last chapter dealing with rational expressions, aka fractional problems. If you have a variable in your denominator, if x is in your denominator, if you want to figure out your domain, you got to set your denominator equal to 0. So in this case, I'd take x minus 7 equals 0. The x value of 7 is the one thing that's going to break this graph. Because if I plug that back in, 7 minus 7 is 0. What are you not allowed to divide by? 0. Therefore, my domain, x cannot equal 7. What that means is we can assume every other x value will indeed work. So if you see a problem with a fraction, set your denominator equal to 0. Whatever value you get for x when you set that denominator equal to 0, that's the thing that's going to break your domain. That's what you're going to write and select from. Now, what about a problem like 23 where you clearly don't see any sort of fraction? In this case, you've got yourself x cubed minus x plus 4. You've got yourself a bunch of regular exponents, which actually makes this a lot easier. So there's no fraction, and you've got yourselves nice normal-looking exponents. If you have yourself an expression, I should say, where all the exponents are whole numbers, starting at 1, etc., 1, 2, 3, 4, 5, 6, whatever the case may be. If that's all you're dealing with, you have an infinite amount of x values that'll work. So we could say my domain is all real numbers. So I can write the little r with the second line in it. That's going to be your domain. 24, we see another fraction, so I'm going to set the denominator equal to 0. Now, you notice in this case, the x is on the top. I don't care if the x is on the top. That has nothing to do with this. We only care about the denominator when it comes to these fractions. 10 doesn't ever equal 0, so this is kind of an irrelevant thought. Since there's no x on the bottom, there's nothing we need to worry about. In this case, we set our denominator equal to 0. It didn't make any sense. That's okay. That just means everything is going to work. All real numbers for our domain in 24. Now, last but not least, we've got number 25, which is the square root of x plus 8. Now, I kind of alluded to this here with problem number 20. Square root graphs are different because they have a clear starting point. There's only so many numbers that you can plug in for x before you get into the world of imaginaries. So, the way that you can figure this out with a square root, you want to figure out what's the first number that will work for x that you can take the square root of, and everything works out. Well, easiest way to do this is to take whatever's underneath the root, set it equal to 0. That x value is the first number that'll work in this case. So negative 8 is the first value that'll work, because if I do negative 8 plus 8, that's 0. I take the square root of 0, and that's all good to go. Every number bigger than that is going to allow me to take the square root of a positive number. Every number less than that is going to make me take the square root of a negative number, and that's going to be a problem. So my domain is going to be x is greater than or equal to negative 8. So I will tell you, you're going to see a couple of things related to this. They're going to be more in a multiple choice format, so you'll kind of have some clues as to maybe what to select from rather than having to pull it off the top of your head. But these are kind of the things you're going to need to look for when it comes to answering questions about domains. Now, last but not least is what you learned in the most recent section, which is how to solve equations dealing with different types of roots. So when it comes to solving equations, the biggest thing you want to make sure of is that you are checking for any extraneous solutions. As you learned in a previous chapter, sometimes mathematically you can get numbers to spit out that don't actually work. So what you're going to want to make sure of is whatever numbers you get, you take a couple seconds, you plug back in using your calculator, making sure things work out all right. So let's talk about 26. You've got the square root of 10 minus n equals 4. Well, we got to get the m by itself. So it's underneath a square root. The way to get rid of a square root, square each side. So if I have a square root of a square, that cancels. I'm left with 10 minus m equals 4 squared, which is 16. We're going to subtract 10 from each side, which will give me negative m equals 6. Divide m by negative 1. That'll get the m by itself. And that'll get me negative 6 as an answer for m. That answer will work. It's not extraneous. It's all good to go. 27 is pretty much the same problem. There's just an x with the equal sign before the equal sign as opposed to a 4 in this case. So we got to get rid of the square root. We're going to go ahead and square each side. So that'll leave me with x squared equals negative 12 plus 7x. Now, this problem, we see two different types of x's. We've seen problems like this all year long. This means this is going to be one of those problems where we got to do a quick amount of factoring. Everyone's favorite thing. So we are going to go ahead and get everything moved to the left side because I want to keep my x squared positive. So I'm going to subtract 7x. I'm going to add 12 and set it equal to 0. So basic trinomial, if you want to figure out what multiplies to 12, adds to negative 7. My two numbers for that would be negative 4 and negative 3. Take each factor, set it equal to 0. X could equal 4 and 3. Now, sometimes where you want to be careful is problems that give you two answers. Sometimes they both work. Sometimes only one of them works. If I do a quick plug in here, if I plug in the 4 in my problem, let's do it under the square root. Negative 12 plus 7 times 4, that's 28. It comes out to 16 underneath. Square root of 16 is 4. X out in front would be 4. That's great. If I plug in the 3, 7 times 3 is 21, plus negative 12 is 9. Square root of 9 is 3, would equal to 3 out front. This case, both answers are actually fine. Nothing's extraneous. They're both good to go. And for our last few problems. So we see here in 28, we've got ourselves a fractional exponent. It's the only thing on that side to do. We don't have anything being added or subtracted or anything weird. So we're going to go ahead and get rid of that exponent. So in order to get rid of a fractional exponent, we take the reciprocal power. So if you see 2/3, we're going to take it to the 3/2. So that's going to cancel out the powers and leave me with x plus 5. Now, you can punch in 16 to 3/2 in your calculator. It'll spit out 64. However, you want to keep in mind one thing. The fact that we have a fractional exponent with an even denominator means there's a plus minus involved. Okay? So if you are doing fractional exponents, okay, or taking roots of things, and you've got an even numbered root, even numbered denominator in your fraction, you need a plus minus sign. That means there's going to be two answers for this problem. So I'm going to subtract 5 from each side. So I'll have negative 5 plus or minus 64. All I'll do is split that apart into two little pathways. I'll add them, and I'll subtract them, giving me two values for x, which will both work, 59 and negative 69. Number 29, similar problem. We've got ourselves 6 equal to the cubed root of 2k. In order to get rid of a cubed root, we're going to cube each side. So 6 cubed is 216. Cubed root and the cube cancel. I'm left with 2k. Not a lot of math here. Divide by 2. 108 is equal to k. And that's your final answer there. Number 30, I have x to the 3 halves minus 20 equals negative 12. First thing we're going to do is get rid of the minus 20 by adding it to each side. So I'll get x to the 3 halves equals 8. And then I'm going to take each side to the 2/3 power. Because again, if I have a fractional exponent, I'm going to take it to a reciprocal power. Reciprocal of 3 halves is 2/3. Since the denominator is an odd number, no plus minus sign here, I'm going to get x equals 8 to the 2/3 power is 4. And that'll get me my final answer. Last but not least, we got 31. We've got square roots on both sides. Well, if I got square roots on both sides, let's square each side to make them go away. That'll give me 2x plus 18 equals 5x. Combine our x's, I'll subtract 2x, so 18 will equal 3x. 6 will equal x. If I check it real quick by plugging underneath, on the left side, 2 times 6 is 12, plus 18 is 30. Right side, 5 times 6 is 30. Square root of 30 comes out pretty gross, but both sides are square root of 30, so it doesn't really matter what that simplifies to. They're both the same. Therefore, 6 is the correct answer. So that is your Unit 7 test review. Everything explained. Feel free to rewind, fast forward, do whatever you need to be prepared for your Unit 7 test.